Are we at time?
Ready to go?
I believe so.
Okay, I'll get us started. Welcome to the fourth webinar in this year's AASHTOWare Pavement ME Design webinar series. The topic of today's webinar is rehabilitation design for fractured jpcp and an asphalt overlay. Next slide, please. I'm Clark Morrison with the North Carolina Department of Transportation and chair of the AASHTOWare Pavement ME Design Task Force. Ari Nair of the Virginia Department of Transportation is the co-chair. Our presenters today will be Harold Von Quintus and Wouter Brink of ARA. Note that the webinar is being recorded and will be available on the ME Design resource website that you can see listed here. Next slide, please. The Pavement ME Task Force provides direction and oversight for development and maintenance of Pavement ME design and the associated suite of tools. Ryan Fragapane is our AASHTOWare project manager, and as mentioned previously, Hari Nair is the vice chair. Other members of the task force are Felix Doucette of the Quebec Ministry of Transportation, David Holmgren of Utah DOT, Patrick Beerle of Ohio DOT, Dulce Feldman of California DOT, and Kumar Dave of Indiana DOT. Suzanne Chan is our liaison with the Transportation Association of Canada. She's from the Ontario Ministry of Transportation. And Tom Yu is our FHWA liaison. Next slide, please. We'll start off with some housekeeping issues. Number one, phones and microphones are being muted. The webinar is being recorded. If you have questions, please post them in the please post the questions in the Q&A box, and this can be accessed by clicking on the WebEx Q&A button. The presenters will answer all questions at the end of the webinar as time permits, and the questions that are not answered because of time will be responded to separately. So all questions will be answered. As I mentioned, this is the fourth webinar in our series. We had two previous webinars on the calibration assistance tool, getting ready for local calibration and completing a local calibration. And we had another webinar on the back calculation tool and recent enhancements to it. And I will note again that all these webinars, the previous webinars were recorded and are available on the Pavement ME Design website. As this one will be as well. So without further delay, I will turn the webinar over to our presenters, Harold Von Quintus and Wouter Brink.
Wouter, you want to do the poll questions to get started?
Yep. Yeah, I was on mute. So I'm going to open the first poll, and I put 2 minutes in there. So we'll. Okay, so the poll should be open now. Okay, about 30 seconds remaining on the poll. Okay. It'll be a couple seconds for some to conclude. And Harold, did you want me to just show the poll results, or we want to do it at the end?
We
I know
can do
that
it
was
at the end.
okay.
Yeah, let's
That
do
sounds
it
good.
at the end.
Okay. So I think
Okay.
that one closed, ready to go.
Okay, thank you. Thank you, Vooter. Today, as Clark said, today's webinar is on a specific design issue of designing overlays of fractured JPCP that has already been, a pavement's already been fractured and asphalt concrete is already in place. With today's webinar, you need to really have prior experience with Pavement ME design, at least the software, as well as the BCT in terms of back calculating the elastic layer moduli, and then also some experience with pavement evaluations for rehabilitation design, those including distress surveys, deflection tests, and subsurface investigations, or the use of cores, borings, ground penetrating radar, and that type of information. So how our last webinar number 3, was on the enhancements that have been made this previous fiscal year to the back calculation tool that's available through AASHTOW. We did not or include where you get the BCT for use. And so this slide just simply shows that it is available within the link to the AASHTOWare purchasing for the other products. And it is included if the agency or organization already has an AASHTOWare Pavement ME license. It is available already. If the organization or agency does not have an active license, there is an annual fee for the BCT itself. If anyone wants the BCT and has any issues, please contact our help desk, and/or you can contact Vooter Brink directly to make sure you get access to the program. Okay, in getting started, we have had, or has previously done many years ago, a webinar. I think it was at the user group meeting, one of the first ones for designing a pavement structure, or not a pavement structure, designing a rehabilitation strategy for a pavement structure that has already been overlaid. As everyone knows, the Pavement ME program is basically confined to one rehabilitation activity. So if the pavement has already been rehabilitated with an asphalt concrete overlay, there still have been questions: how do we design the second, third asphalt concrete overlays for the pavement in question, which has already been overlaid? And we have also, the help desk has also received questions on kind of recently on how to design an asphalt overlay of a fractured PCC pavement, especially in initially using the BCT to back calculate elastic layer moduli values. And how can that be done integrating the BCT with the Pavement ME software? So we thought since we were receiving additional questions, the task force as well as AASHTOWare thought it might be good to have a update on helping answer questions for day-to-day practice for pavements that already have been rehabilitated with an asphalt concrete overlay. So the intent of today's webinar is basically not to go through the software itself. In other words, this is not training on the software per se, but it is the intent of the webinar to determine inputs as well, more importantly, to make decisions in using results from both the BCT and Pavement ME design for setting up a rehabilitation design of a fractured jointed plain concrete pavement that has already received an asphalt concrete surface. In other words, it's already been fractured and this has been placed, and time has passed by where an additional rehabilitation strategy or another rehabilitation is in order. So that's really the intent of today's webinar. Our learning objectives, basically 6 of them, applying results from the back calculation tool, evaluating results from that back calculation tool in terms of elastic layer moduli and other responses or parameters from the back calculation tool for use in rehabilitation design, and simulating a fractured jointed plain concrete pavement that already has an asphalt surface for rehabilitation design. Select an appropriate rehabilitation input level, and then determine load transfer efficiency of that existing overlaid fractured concrete pavement. And then a little on reflection cracks calibration coefficients for inner layers that has recently been done for a couple of agencies, and I'll get into that obviously later. So the outline of today's webinar, we first of all want to go through a description of the existing pavement. This is a real design, but it's going to be noted as a generic pavement design or rehabilitation design. We'll go through applying results from the back calculation tool, a little on rehabilitation analysis type or rehab input levels when we have an existing asphalt overlay already in place, inputs for rehabilitation design, and then the outcome or results from the rehabilitation design, and then obviously go through the question and answer session toward the end. So we're going to start first of all with the description of the existing pavement. As I mentioned, the jointed plain concrete pavement was originally constructed, I think it was in 1976. In 2001, it was originally fractured, the plain jointed concrete pavement, and then was overlaid with an asphalt surface in 2001. Over time, that asphalt overlay started exhibiting some cracking, and some of those transverse cracks are beginning to exhibit moderate deterioration around the cracks. So the current asphalt overlay that's in place is exhibiting cracking and then some moderate deterioration around those cracks that have developed, predominantly transverse cracks. FWD or falling weight deflectometer tests were done to back calculate elastic layer moduli. There were some cores or borings completed for the preliminary rehabilitation design. Ground penetrating radar was completed for layer thickness determination. And then there was a distress condition survey that had been completed to determine basically the condition of the surface in terms of the type of distresses their condition as well as severity level. The details of the existing pavement, this is kind of a summary that comes from the borings that had been done or were done along the project site for a preliminary rehabilitation design. And so I just kind of go through those. Some of the borings did exhibit, or there was a rigid, stiff layer on some of the borings, not all. There is an embankment soil. It's a fine grain soil over an existing fine grain soil. And that was September 1976 construction date. The aggregate base, there is an aggregate base there. The initial construction, obviously 1976, that varied in thickness from 4 to 8 inches. The jointed plain concrete pavement was originally constructed in 1976, and the boring showed it to be somewhere between 9 to 10 inches in thickness, predominantly closer to 10 inches overall. And then the asphalt overlay, it's fairly thick asphalt overlay, was originally placed in 2001 after the slabs had been fractured in 2001. That overlay thickness consisted of obviously various lifts, but the overall thickness of that asphalt overlay varied from about 7.5 to about 9.5 inches. Overall average thickness was about 8 inches in thickness along the project. Excuse me, this is simply an overview of the asphalt overlay, the different layers that had been placed. There was a leveling course that was placed about 2 inches, and intermediate layers were placed of about a total of about 4 inches, and then a wearing surface of a PG 64 minus 28 of 2 inches, all placed in 2001 after the slabs had been fractured. This is kind of just shows a schematic or photo of a few cores in terms of and this table summarizes the overall condition of the asphalt or the pavement surface for the preliminary design. Rut depths were very minor, average only about 0.2 inches. Transverse cracks also weren't that significant, about 450 feet per mile across the entire project on the average of about moderate severity level or medium severity level. Fatigue cracks, there were some fatigue cracks that were present or are listed, but the area of those cracks were generally less than 5% along the entire project, and those would be considered minor or hairline from the distress surveys. Now, that was a description of the existing pavement, and now we'll go to using the back calculation tool and or applying the results from the back calculation tool. As a reminder, we're not going to focus on how to use the BCT. This isn't a training session on using the back calculation tool. The intent of this webinar is how to use and interpret the results from the BCT for the rehabilitation design. And so that's basically what we're going to cover. So this is from the back calculation tool, those that have used the tool for evaluating pavements in preparation for rehabilitation designs and or for rehabilitation designs. This is a screenshot from the program that shows the deflections along the project, the surface deflections under the loading plate. And then the lower graph displays the layer thicknesses for basically the asphalt concrete surface and then the aggregate base. This is from GPR related measurements. For the graph here, The thickness of the concrete's not shown because it was fairly consistent along the entire project. So this is just a schematic of how the layer thicknesses of the asphalt concrete overlay and the aggregate base are varying because there was more variability in those two in consideration with the variation of the deflections under the FWD loading plate along the project. The lower right-hand side here, this shows the layer structure from the BCT for those measured along the entire project. There were generally 4 layers. Obviously, layer 1 is the asphalt, dense graded asphalt concrete overlay. Layer 2 is the fractured jointed plain concrete pavement. Layer 3 was the aggregate base. And then layer 4 is the fine grained subgrade soil. And these come directly from the GPR thickness measurements that were made along the project, and then those were imported into the back calculation tool, as well as the FWD deflection basins themselves. Now, the back calculation, as everyone knows, back calculation, the BC2T is limited to 5 layers. As a reminder, EverCalc from Washington State is the engine in the back calculation tool. And we always like to thank Washington State for allowing AASHTOWare to include EverCalc in this tool for use in rehabilitation design. But in using or in doing a back calculation tool for the structure that exists in place for this project, there are some questions that always come up. These are the questions specific to this specific project. And the first is that 8-inch aggregate base that's located below basically 16 inches of asphalt and a Portland cement concrete slab and insensitive layer. In other words, we have on the average about 8 inches of asphalt overlay, and that's over about 10 inches or so of an somewhere between 9 and 10 inches of an insensitive layer. So, you know, that's the relative thickness of the aggregate base would be considered a thin layer and would probably be very insensitive to the deflections or FWD deflection loads. But the question is that an insensitive layer? And then the other, since some of the borings did show a rigid layer, should we include layer in the BCT analysis? Third question, is it really necessary to subdivide, or should we subdivide the PCC layer into 2 layers with the crack and seat fracture method? And then the fourth is, should the existing asphalt concrete layer be subdivided into multiple layers, or say 2 layers, or simulated with just 1 layer in the back calculation tool, as well as in the Pavement ME design strategy for rehabilitation design? So these are some of the questions that were asked initially, and then we'll go through kind of each one. So the first is, should the elastic modulus of that 5 to 9 inch aggregate base layer be back calculated, or should that layer be fixed? In the manual of practice, there is a rule of thumb that, as well as in the user guide for the back calculation tool, there's a rule of thumb that the elastic modulus, or any layer beneath the surface that is significantly less than the thicknesses of the upper layers, that layer should be fixed with a specific elastic layer moduli. In other words, the elastic layer modulus not be back calculated with the BCT, but that layer be fixed. And so we'll go through some results of allowing the BCT to back calculate the elastic modulus for the aggregate base in accordance or coming back to that rule of thumb that's in the manual of practice and or in the BCT user guide. So this simply shows using the BCT and back calculating the elastic modulus of the aggregate base. This is also simply a screenshot from the BCT showing how that elastic layer modulus varies along the roadway or this project site for the aggregate base. And you can see that along this project, there are sections where we're hitting the upper boundary condition that was set of 200 KSI for an aggregate base, as well as hitting the lower boundary modulus of 10 KSI. So that's a very extreme variation of an aggregate base along the project. This shows now just a screenshot of the summary of the aggregate base as well as the elastic layer moduli of the other layers. What I want to focus on is the granular base or the crushed stone. It had on the average across the entire project about 100 KSI. The coefficient of variation was very large, 85%. So the aggregate base has a lot of variation and goes from the minimum to the maximum boundary value, as I shown on the previous screenshot from the BCT. So that's a lot of variation along the aggregate base. So the question, is that a real variation, or is it simply the variation a result from an insensitive layer? So breaking the, fixing the aggregate base, not having it back calculated, but the BCT was used to fix the aggregate base modulus from 30 KSI to 100 KSI. And then the layer moduli for that condition were back calculated for the asphalt overlay, the fractured jointed plain concrete pavement, and then the subgrade soil, as well as the with the bedrock located beneath the surface. So you can see that as the fixed base modulus of the aggregate base goes from 30 to about 100 KSI, over 3 times different, you can see there's not a big effect, almost no effect on the asphalt overlay, back calculated elastic modulus, very little impact on the fractured jpcp, and very little impact on the back calculated elastic modulus for the subgrade soil. So from the results of the BCT back calculating and then fixing it at different levels, the aggregate base has a very high coefficient of variation and really has little impact on the other elastic layer moduli that were back calculated. So in summary, the decision would be to fix the aggregate base modulus at the typical laboratory-derived modulus we would measure in the laboratory, or simply use a default laboratory-derived value aggregate base layer. Okay, so this kind of just gives justification for the rule of thumb that was included in the user guide and or the manual of practice. We're not saying that or suggesting that for every project a user would have to go through both, back calculating and then fixing the aggregate base material. There are rules of thumb in the back calculation user guide, as well as in the Pavement ME user manual. in setting up pavement structures that obviously exceed 5 layers, or the limit of 5 layers for the BCT as well as for EverCalc, and then how those layers can be simulated in the tool back calculation tool for use in rehabilitation design. In fact, for this project, the aggregate base was originally just fixed because we were fairly confident that that this was an insensitive layer, and so we're showing these just to indicate that yes, the decision to make it an insensitive layer was justified. Okay, next question, or the second one. Is a rigid layer present along the design segment? We know it was from some of the borings that had been done that identified, as well as some of the Soil Conservation Service series maps within this area, that there is hard pan or layers that would be simulated as bedrock or fractured limestone near the surface. And so the BCT was used to back calculate the depth to the bedrock. As kind of as a reminder, this was one of the enhancements that was made to the BCT that we went over during webinar number 3 of this fiscal year. This is a screenshot from the BCT simply to show the results from that the BCT in terms of calculating the depth of bedrock along the project. And you can see there are distinct areas where bedrock is close to the surface, about 120 inches of subgrade depth or thickness. And then there are other areas where it is well below the surface, over 600 inches. And the assumption of simulating bedrock is not there would be okay, or would be adequate. So, but it does vary along the project where we have a hard pan or a very stiff layer closer to the surface. So this is going to be used in the back calculation tool to then calculate or back calculate the layer moduli for of the other layers associated when hard layers near the surface versus when it's very deep. But we are including the rigid layer in the back calculation structure simulation from these results. Okay, the next question, should the fractured PCC slab be simulated as 1 layer or 2 layers? The reason this question is asked sometimes is it's predominantly for rubbleization, but for this project, it's not rubbleization, but it's crack and seat of a concrete pavement. And the different, the distance between the cracks or the fractures is about 3 feet along this project. So for a jointed plain concrete layer, generally it's kind of common practice just to consider that as 1 layer. For the jointed reinforced concrete, there are situations where it's better to simulate that jointed reinforced concrete pavement as 2 layers, even for the break and seat method. For rubbleization for jointed plain concrete pavement, sometimes it's better to simulate into 2 layers. It is 1 or 2 layers. With jointed reinforced concrete pavements that are being rubbleized, it's generally best practice to simulate that as 2 layers. 1 layer above the reinforcing steel, the other layer below the reinforcing steel. Obviously, the simulation is dependent upon the agency's specification for rubbleization and or the agency's specification for the fracture method. whichever one is used. So in answering the question, we used the BCT to basically calculate the elastic layer modulus of the fractured slab into 2 layers. And this simply shows a screenshot from that process to answer the question, should the fractured PCC slab be simulated as 1 or 2 layers? And the slab was subdivided at the mid depth between its overall thickness along the project. And this shows the results. The orange is the lower layer or the upper layer. The green shows the back calculated E values for the fractured below on the lower layer. Orange is the upper layer, green is the lower layer. And you can see they kind of transition back and forth. If we do an overall average, which the BCT also does, this is also a screenshot. This shows the average back calculated moduli for those 2 layers, as well as the coefficient of variation. So in summary, this would also be consistent with the rule of thumb that for crack and seat of jointed plain concrete pavement, it's usually best practice or common practice to simulate that as 1 layer, because there really is no consistent or significant difference between the 2 PCC layers along the project. And you can see that there is, the upper was about 1400 KSI, the lower about 2400 KSI, but the coefficients of variations are extremely large, well over 100%, a lot of variation. So really, are they statistically different? So in summary, the suggestion would be consistent with the rule of thumb in the user guide and or manual practice to simulate the fractured jointed plain concrete pavement as 1 layer. And that's exactly what was done. Okay, so next question, should the existing asphalt layer be simulated as 1 or 2 layers? For many overlay projects of rubbleized PCC layer, crack and seat PCC layers, as well as overlays of existing asphalt concrete surfaces, where that overlay can be and should be subdivided into 2 layers, because some of the lower layers may be exhibiting moisture damage or some type of deterioration in that layer itself. So it's better practice to subdivide the asphalt overlay into 2 layers, and that subdivision between the layers would be dependent upon the results from borings and or cores that were done along the project. This just shows kind of a summary or an overview of the typical, let's say, asphalt concrete core recovered from the project. No signs of deterioration or moisture beneath the asphalt surface. So if there's no observed or designated moisture damage, no mixed deterioration through the core, we would simulate as 1 layer. If there is moisture damage or mixture deterioration, then that asphalt core in general should be the asphalt layer should be subdivided where the layers that are exhibiting deterioration and or moisture damage. So we would simulate it as 2 layers. This shows the results now. This is a screenshot from the BCT, and this is using the BCT to calculate the elastic layer moduli of 2 layers of the asphalt concrete overlay, similar to what was done for the Portland cement concrete fractured slabs. The blue shows the surface, the upper surface. The orange shows the lower layers in the asphalt concrete overlay that was placed in 2001. And so this is no consistent difference. Again, this is just a screenshot from the BCT. And this is also a screenshot from the BCT summarizing the results by grouping or subdividing the asphalt concrete into two surfaces, the wearing surface and the lower layers. I think this had a PG of 64 minus 28. This was a PG grade 64 minus 22. So you can see this is about 3 KSI, pretty high modulus. And the lower layer was about 2,800 KSI, almost identical values. So there's certainly no statistical difference between the two. So summary, no consistent or significant difference between the two asphalt layers. Also, cores do not show a difference between the asphalt layers. So the results from the FWD testing, back calculation with the BCT, and cores provide the same observation. So in summary, we simulate the asphalt overlay as one layer in this example, in this problem, or in this rehabilitation design. So in summary, the 8-inch aggregate base, it is an insensitive layer, so we treat it as an insensitive layer. Should a rigid layer be included? Borings as well as the FWD and BCT results found a rigid layer, and so yes, for some of the sections that do exhibit that rigid layer close to the surface. Is it necessary to subdivide the PCC layer that's fractured, the PCC slabs, into 2 layers? The answer is no, and that's supported by the FWD deflection testing, as well as the rule of thumb, the suggestion for the rule of thumb. Should the existing asphalt layer be subdivided into multiple layers or just use one layer? It's no, they shouldn't be subdivided. One layer should be used, and that's to be consistent with the results from the FWD testing and the BCT, as well as supported by the cores that were removed along this project to look at and evaluate the asphalt concrete overlay that had been placed in 2001. So moving on now with the BCT, how do we subdivide the segments for rehabilitation? Should we use one back calculation for the entire project, or should we subdivide or segment the project into different area design segments or design sections? So the depth to the rigid layer, since it is significantly different and there are some abrupt changes along the project, the depth to the rigid layer was initially used to identify the design segments to be used for rehabilitation design, kind of as a practical variable. Also supported by the results from the borings and what is beneath the surface along this project from the Soil Conservation Service series in the areas. So this just shows, this is a screenshot from the BCT showing the areas that were segmented along the project. And there were 6 of them. This is the first one, segment 1, then segment 2. Segment 1, the hard layer or rigid layers near the surface. Segment 2, it's well beneath the surface. Segment 3, it's closer to the surface. Segment 4, it's well below the surface. 5 is below. I think I got those reversed. It's the bedrocks are very below the surface, near the surface, well below the surface, near the surface, well below the surface, near the surface, well below the surface. So there's 6 of them. And again, this just shows the deflection along the project under the loading plate. This are the layer thicknesses of the asphalt and the aggregate base along the project. And this shows on the table on the lower right hand shows the different layers as defined from the ground penetrating radar results that were done in concurrence with some of the borings that were done along the project to also measure layer thicknesses. This is now simply the results. Show 2 examples, segment 1, segment 4, along the project. And this is also screenshots from the BCT. What we're going to kind of focus on is the asphalt average asphalt modulus, kind of the coefficient of variation in the thickness. Asphalt overlay segment 1, about 9 inches, 2,300 KSI, 56% coefficient of variation. The fractured, a little bit over 1,000 KSI, a little bit over 1 million. Crushed stone is a fixed layer. For the back calculation, it was fixed at 50 KSI. The subgrade soil in the segment 1 was 52 KSI, and its thickness was about 120, a little over 120 inches. Segment 4, and this is where the hard pan or stiff layer is close to the surface. Segment 4 is where it was well below the surface, or the rigid layer or stiff layer. Again, asphalt concrete back calculated, very close, about 2,300 KSI. The fractured jpcp in this area was about 600 KSI, a little over 600 KSI. Crushed stone was fixed at 50 KSI. The back calculated modulus for the subgrade soil was about 34 KSI. And its thickness was well over 500, close to 600 inches predominantly along this segment number, defined as segment number 4. In summary, this shows the results of all 6 segments. And the upper table here shows the elastic layer moduli calculated for each segment by layer. The lower table shows the layer thicknesses, the average layer thicknesses from the GPR results, with the exception of the thickness of the soil, and that comes from the back calculation tool itself. So you can see for the asphalt overlay, there's not a big difference between all of the segments. The fractured jointed plain concrete pavement, there is. For segments 1 and 2, it's about a little over 1 million PSI or 1,000 KSI. But on segments 3 through 6, they're well below that, and they generally vary from about 500 to about 700 KSI. So that's a difference. Aggregate base was fixed at 50 KSI. And now this shows the soil back calculated, and show for segments 1 and 2, it's above 50 KSI back calculated value. Whereas in segments 3 through 6, it's between, say, 30 to slightly less than 40 KSI. And so that's a fairly large difference, or a difference, and these are back calculated values from the FWD deflection measurements. The thickness is, you can see that there's no consistent high versus low thicknesses for the asphalt overlay, about 8 to 10 inches for segments 3 through 6, about 9 inches, segments 1 and 2. The fractured PCC is closer to about little over 10 inches. The aggregate base is relatively thicker in segments 1 and 2 and thinner in segments 3 through 6. The soil, segments 1 close to this was hard pan or stiff layer was closer to the surface versus segment 2. Segments 3 through 6, there were some where that stiff layer was located closer to the surface, like in segment 3, and very deep, like in segment 4. So the big thing is the fractured PCC does vary consistently between segments 1 and 2 and 3 through 6, as well as the subgrade soil elastic modulus for segments 1 and 2 versus 3 through 6. So in general, there is a response difference between segments 1 and 2 versus 3 through 6. Kind of keep this summary in mind. In a couple of slides, I'm going to come back to a difference between these two segments or between these different segments 1 and 2 versus 3 through 6, and setting up or deciding on a rehabilitation strategy. So kind of keep this in mind, that there is a weaker subgrade, segments 3 through 6, a weaker, a lower elastic modulus for the fractured PCC slabs along the project. This now is, I'm going to come back now to the BCT, and this is why we get some of the questions regarding the back calculation tool and with the pavement ME design is how do you do a rehabilitation design for a project that has already been overlaid? Because this is a screenshot from the BCT, and we have a layer 1 is the asphalt overlay. That's not shown in here, but it's an asphalt overlay. And we have the fractured jpcp, crushed stone, and then a subgrade soil, and then the bedrock. And if we tried to export the results from the back calculation tool, if we try to export those results in setting up a pavement ME design file for setting up an analysis type, we would get an error term. So if we're done with the BCT, now we want to export those results to the pavement ME, export it to pavement ME, we would get an error because pavement ME is, from what I said earlier, is not applicable to a design strategy that already has for strategy and asphalt concrete overlay already in place. So all that means is we can't export it and automatically set up a pavement ME design file. So we would have to manually set up that pavement ME design file itself. So this is for segment 4. And so all that means now is we can't do it automatically or have the program do it. We're going to have to do it manually. So now I want to move to the, with results from the BCT, our rehabilitation analysis type for pavements with an existing asphalt overlay. I would like to make one correction from what I just said. There is a rehab strategy where you can have an asphalt wearing surface at the surface and do an asphalt concrete overlay. And that is a semi-rigid pavement where we have an asphalt for new construction. We have an asphalt wearing surface over a cementitious stabilized base or some cementitious cement stabilized layer on subgrade. And the program will allow us to design an overlay for that condition. And we can, or the user would be able to automatically have the program transfer the results from the BCT to a pavement ME file and initially set up that file based on the results from the back calculation tool. But that's the only strategy that you're allowed to do that. So the rehabilitation analysis type for pavements with an existing overlay. I'm coming back now to the rehabilitation input level. Which one should be used? And this is rehabilitation input level for our existing pavement structure. And this is in accordance with the manual of practice that's discussed in chapters 9 and 12, basically in the manual of practice. So we have a rehabilitation strategy input level. And we know that for asphalt overlay, AC over AC, that's where we're going to have an asphalt overlay over a flexible pavement, as well as an asphalt overlay of semi-rigid. We have rehab input level 1 that we can use, which is non-destructive testing. In other words, we're defining the elastic layer modulus based and the condition of the existing layers based on falling weight deflectometer testing and back calculating the elastic layer moduli. Input level 2 for AC over AC or AC over semi-rigid is simply using the distress surveys to estimate the structural condition of the asphalt overlay itself in place, or the asphalt wearing surface or asphalt layers that are in place. So they're kind of like remaining life is defined based on the distress surveys, fatigue cracking, and other distresses, and not non-destructive deflection testing. Rehab input level 3 is simply defining the quote remaining life or structural condition of the existing asphalt concrete wearing surface based on a ratings from 1 to 5. And the manual of practice basically, and the other webinars we've done, we've recommended that in most agencies have the necessary data in their files where they should never need to use rehab input level 3. In fact, it's suggested that rehab input level 1 or rehab input level 2 always be used for rehabilitation design, where we're designing an asphalt overlay of a flexible or an asphalt overlay of a semi-rigid pavement. For AC over JPC intact slabs, in other words, they're not fractured or rubbleized, AC over CRCP intact, AC over JPC or JRCP fractured, that's the crack and seat or the break and seat. The rehab input level is there are no different rehab input levels. It's basically all one in using the pavement ME design strategy. So there's not an option for rehab input level 1. Obviously there's not a option for the different rehab input levels. So obviously what we're going to do, we're using the asphalt overlay over a fractured jointed plain concrete pavement as our design example. AC over PCC that has been rubbleized, either JPCP, JRCP, or CRCP, this would be simulated as a new asphalt pavement in accordance with the manual of practice, the pavement ME manual of practice. So we're going to focus, this design example is AC over fractured slabs. So with that, then I'm going to move to the inputs for rehabilitation. Kind of as a reminder, the intent of this webinar is how do we determine the inputs for rehabilitation design for that fractured jointed plane concrete pavement that has already been overlaid. The intent is not on how to use the Pavement ME software itself. So we're making decisions, interpreting data for deciding on inputs to Pavement ME for designing the second and or third overlays of an existing pavement that has already been overlaid. This specific pavement is a fractured jointed plane concrete pavement, as mentioned at the beginning. So the first thing is we got to set up the pavement structure and overlay. And in doing that, we've received, previous common questions. And some of these common questions are, what C factor should be used to determine the resilient modulus of those unbound layers? Second, common question, what is the overlay construction date? Because remember, Pavement ME only allows one. In reality, for this project, we have two overlay construction dates. And then the third question, what asphalt overlay property should be used to simulate the existing asphalt overlay? And we're going to kind of go through each one, take each one individually. So first of all, we're going to start with the C factors. And this is table 10.10-8 from the Manual of Practice, the Pavement ME Manual of Practice. And we're going to use the C factors to determine elastic modulus of the unbound layers. And for the subgrade soil, there's generally what we have is we have an AC and PCC layer above the subgrade, and we have an unbound aggregate base layer, but that is treated as a insensitive layer. So should that have any impact or impact on our decision for deciding whether our C value should be 0.52 in accordance with the Manual of Practice or 0.35 in accordance with the Manual of Practice? And so this is, and for the C factor, the asphalt overlay, and for this one segment, 10 inches on the average. Fractured PCC is 10.3. These are the elastic layer moduli. The aggregate base is 5.6. This is the back calculated layer modulus, and the soil resilient modulus of 574 of the thickness of which was an A4, is 34 KSI on the average through this one segment. And so the C factor for the asphalt overlay is not applicable. The fractured PCC is not applicable. The aggregate base, we're saying the C factor is really not applicable. It really should come from the, because we just selected this value as a fixed value in the back calculation process because it had its final value in terms of back calculating it had almost none to very little impact on the other layers. So this should be a lab derived or default value that is representative of the condition of the aggregate base in place that we had. So the C factor is not applicable for the soil. Since the information we had, it did not indicate that the aggregate base was saturated and or contaminated with subgrade fines, we elected to use a default value that would be a value you would measure in the laboratory at the optimum water content and max dry density for this aggregate base. So the aggregate base that was used was 25 KSI. That was an insensitive layer, and we're using the default and or laboratory derived modulus value, and this really should be 25 KSI rather than 30 KSI. I'll have to change that after we get through with the presentation. That's a typo. It should be 25 KSI. One of the things I wanted to mention here, though, an agency, a user, consultant could use dynamic cone penetration test when we do have insensitive layers. In other words, we got a relatively thin aggregate base below whatever's at the surface or the bound layers, as in this condition. And we can use the DCP results to determine what the stiffness or in-place stiffness of the aggregate base is from the penetration index itself, using the dynamic cone penetrometer. So that is an excellent use of the DCP if it is available in determining what the modulus should be in place of those when we do have an insensitive layer from FWD deflection basins. Fine graded soil, it's 11.9 KSI. And we would use the VAV-C value below an aggregate base. That's the value that should be used, 0.35. The 0.2552 below an AC or PCC layer should really only be considered when that aggregate base is very much contaminated with clay fines and or saturated. In other words, it's not really responding to loads as an aggregate base material. It's responding more like subgrade soils where it is contaminated and or saturated. So 0.35 was used. So subgrade soil, the resilient modulus, this is a screenshot from Pavement ME. It's 11,900 PSI was used, and it is an A4 subgrade soil. Now, since we're using the back calculated elastic layer modulus value with subgrade soils, most of you should remember that one of the keys or one of the gradation or other engineering properties that should be used in Pavement ME, and this is a screenshot for that A4 fine graded soil from Pavement ME, we should use the average water content of the subgrade soil during FWD testing for the sections that the FWD test apply to. These would apply to segments 3 to 6, that's the lower resilient modulus value of somewhere between 30 and 40 KSI from the FWD, and its value from the borings that were recovered, material recovered from the borings, was about 13.5% on the average. So that water content is now entered into the Pavement ME, not as the optimum value, but as the in-place value that would be consistent with the back calculated value from the FWD deflection basins, shown in this screen. So that's just to ensure that the volumetric properties are consistent with how we determined the in-place resilient modulus for this layer. Moving on down to the aggregate base layer. This is the 25 KSI, it's the insensitive layer. And so this simply was the default value for the aggregate base layer that was for this type of material within this organization, let's say. Okay, so it's 25, and then for the gradation and other engineering properties, it would be the default values that are consistent with the default resilient modulus value for this crushed stone or this A-1-A Ontario. Now moving on to the load transfer efficiency, which is another input for Pavement ME. This is the fractured jpcp, which is going to control the load transfer efficiency and elastic modulus. So this is table 913 in the manual of practice that we're going to refer to. And the load transfer efficiency can either be measured or it can be tied to crack severity. So we're going to go through each one. First of all, from the BCT, we can calculate, or the BCT does calculate the load transfer efficiency if it is measured in accordance with across cracks, like transverse cracks in the existing pavement. And so in this specific case, it was, we have the deflections measured at the -12 sensor as the numerator, and then the deflections under the loading plate, which is the denominator. And this simply shows the calculated load transfer efficiency throughout the pavement project or throughout this rehabilitation project in accordance with calculated in accordance with the 93 or through LTPP. This would be in accordance with the LTPP procedure. And that's what was used within the back calculation tool. And as you can see, there's a big difference between these now are segments 1 and 2, where we have these very high load transfer values, and then versus 3 through 6, which have much lower average load transfer efficiencies along the project. Then this is a screenshot, as I said, from the back calculation tool. The other very important item, which now I always look at, would be the void intercept. This is also done with the BCT software. And you can see that segments 1 and 2, well, before I note that, the void intercept was basically set up for testing Portland cement concrete pavements to look at the potential for voids. And this intercept is determined in accordance with how it's typically or has been calculated with the 1993 AASHTOWare design guide. So they're the same, or they're similar, if not the same. So the important point here is you can see that there's a big difference between the first two design segments versus segments 3 through 6. And the void intercept, I'm now starting to use as an indicator on what may be going on, even when we have an asphalt concrete surface and on a flexible pavement, and we do deflection testing. Do we see a difference between this void intercept along the project? We have noted in some conditions that this void intercept and I don't want to say that this is always the case, but we've noticed that it can be the case, or we can see a big difference in this void intercept between areas where we have no stripping versus areas where we may have stripping, maybe layer debonding between different layers, and or deterioration of the underlying asphalt layers. So that was used on this project to see there appears to be a big difference. What's interesting on this first part, segments 1 and 2, is that the deflections measured under the loading plate on the loading plate side of that crack, transverse crack, are less than the deflections measured at the -12 loading sensor, or within the segments where the -12 sensor deflection is greater than the deflections under the sensor plate. This first segment is also where we have the hard layer closer to the surface, but we do have hard layers closer to the surface within these other segments. So, but there is something else going on within this pavement structure that there was insufficient data to try to identify what's causing this specific condition between segments 1 and 2 versus segments 3 through 6. Okay, now this is the low transfer efficiency, but we're defining the severity level. We're not using the FWD. We're defining the severity level based on whether the crack severity levels are low, moderate, and severe. And for the fractured, jointed concrete pavement with transverse cracks, the crack and seep method, that default values when you just have crack severity is 50%. And that almost coincides with the calculated through the BCT for this condition, for this project, where the average LTE within segments 3 through 6 was about 45%. So they were very close between input levels 1 and 2 for defining load transfer efficiency. Obviously, there are cases where that will not be the case. For this project, that was found to be the case. So for entering or simulating the jointed plain concrete pavement, fractured, the low transfer efficiency, the 50% low transfer efficiency was used. Crack spacing of 3 feet was used. And then the average for this segment, this is segment 4, was 616 PSI as the average back calculated modulus. And the thickness was 10.3 inches. Now, a little on the asphalt overlay properties were used in rehabilitation. And this is where we start getting into some questions, since we're going to have 2 asphalt overlays. This first one placed in 2001, and then the second one going to be placed in 2022. How do we simulate that in Pavement ME? We know for the first overlay that is going to be aged or represent age condition depending on what is milled. So we may have an upper or lower asphalt layers, especially of cores. Our deflection testing suggests different responses. In this case, that was not the case. It's simulated as one layer. The second overlay, or the one to be placed in 2022, we know top-down cracking can be an issue. And so if we're placing a thick enough asphalt overlay, will we have a wearing surface and lower asphalt layer, where this second overlay should be simulated with 2 layers. Through Pavement ME, and I didn't note this on this slide, but there's for the asphalt overlay, especially of fractured slabs or intact Portland cement concrete slabs, the Pavement ME software limits the user to 3 different asphalt layers for the overlay. So that either means we have 1 layer here and up to 2 layers of the overlay of the first overlay, or we can have 1 layer of the proposed overlay and then 2 layers for the first overlay that was placed in 2001. And as I noted earlier, we're only going to have 1 asphalt layer in 2001, because that's what all the data in the core suggest. So that's exactly what was done. And then the second overlay then can either be 1 or 2, depending upon the thickness of that overlay, on whether we want to simulate 2 different lifts or 1 overall asphalt overlay to be placed. So the existing asphalt pavement This is also, I didn't mention this earlier, but this is another item that we can look at. The existing asphalt overlay, the back calculated values were, and this is the existing overlay that was placed in 2001. The back calculated values, as you remember, is about 2,200 to about 2,500 KSI. That was the back calculated, not a lot of variation. The laboratory derived, if we had good material, undamaged, now this has to do with the undamaged versus the damaged master curve in Pavement ME. If we take that default master curve and then we just look at the laboratory derived E values for the frequency of 30 hertz from the FWD, at the same temperature levels, and the temperatures, I didn't mention it previously under the FWD, but the air temperatures or surface temperatures were about 57 on the average, 55, 57. That's the surface temperature. The air temperature on the average was about 42, 45 degrees Fahrenheit. And so if from that, the frequency and temperature, if you take that default and you look at what the master curve will give us, it'll be somewhere between 2,400 and 2,800 KSI beneath the surface. And so that's very close to the back calculated values. In other words, they're basically within the same range. So no structural deterioration or mixed deterioration defined by the FWD deflection basins or back calculated values. So we're assuming no structural deterioration and or mixed deterioration where our back calculated values would represent a damaged master curve. The back calculated master curve is almost very similar to the undamaged lab derived master curve. So the decision is that's exactly what we're going to use. We're going to use the undamaged master curve within the Pavement ME. And that's the input shown here for Pavement ME. The thickness, our original preliminary design was go ahead, let's for segment 4, mill out 3 inches to remove some of the immediate moderate transverse crack severity that occurred at the surface. So for that thickness, we'll have about 7 inches left after we mill. We're using the air voids and the binder content that are defaults for this layer that was placed in 2001. You'll see in a minute why I'm making that decision. The aggregate gradation parameter is for this existing. And then the binder for this layer is the PG 64-28 that represents the existing asphalt wearing surface layer. Okay. The second asphalt layer is our overlay placed in 2022, to be placed in 2022. Has a thickness of 3 inches. So this is going to be a kind of like a mill and replace, remove 3 and replace with 3. These are the default values for this new overlay. 7% air voids, total percent asphalt content by weight about 5.6. The aggregate gradation parameters that are determined from the gradation. The new binder for the new overlay is a PG 70-28. And we're assuming 1 layer. So we're not breaking it up into 2 1.5-inch layers. Since everything is the same, we're just simulating a 3-inch layer for the second asphalt overlay to be placed in 2022. So this is the overall preliminary design. We have an asphalt overlay going to be placed in 2022, 3 inches. We're milling 3 inches of the existing surface. So the original asphalt overlay in segment 4 was closer to 10 inches. And so that's the reason we have 7 inches left. The fractured slabs are 10.3 inches. This is along the entire project. And then the aggregate base was about 5.3 in segment 4. And compacted soil for segment 4, I think, was not the compacted soil, the existing soil was about 600 inches, or I think it was 574 inches, or there was no rigid layer close to the surface. So that's our cross section. The next question is, what is our overlay date? The rule of thumb for the date to be established in Pavement ME, because there's only one pavement overlay date, which ones, is it 2001 or is it 2022? In this specific example, our rule of thumb is if the thickness of the overlay remaining, now this is the overlay that was placed in 2001, is greater than the thickness of the new overlay to be placed in 2022, set the date for the first overlay and use the maintenance strategy. So that is the case here. We only have 3 inches of our new overlay. We have 7 inches of the existing overlay, previous overlay remaining in place. So that means I set the date to 2001, when the slabs were originally fractured and the first overlay was placed. So it's all in 2001. So that means our design overlay is 21 years for the existing overlay, and then a 20-year design for the new overlay. So that's a total of 41 years. The thickness over the overlay remaining less than the thickness, if the thickness of the overlay remaining, let's say only 2 inches remained after we milled, and the thickness of our new overlay was going to be 4 inches, then the overlay date here would be the overlay date for the new overlay, whether that's 2022 or 2023, whatever the date of the new overlay is. But these are rules of thumb that are covered in the manual of practice. So the date of the overlay, first overlay, 2021 with a 21-year, 41-year design life, and we're resurfacing at 22 with a maintenance strategy though, because we're still overlaying it in 2022 where we're milling. So all the rut depths are being removed, the surface cracks, the high, moderate severity, medium severity transverse cracks are being removed. And then our second overlay is being, placed 2022 with a 20-year overlay date. So with that, what is the maintenance strategy and why are we using a maintenance strategy in this example problem? And as I mentioned earlier, I'm going to go back very briefly. We're placing an overlay in 2022 with milling. So that means the rut depths are being removed, the moderate severity cracking is being removed. So how do we account for that in Pavement ME, even if we're not doing a maintenance strategy? So even though this isn't, let's say, directly simulating what's happening, it gives us a option in Pavement ME that we can consider, or we can reset the non-structural distress values for the overlay placed in 2022. And you'll see that to be the case in just a minute. And so what I've done here is I said yes, and this is a screenshot from Pavement ME. I'm going to use the pavement preservation maintenance activity, the month and the year, so it's 2022 is the important one. It's a non-structural overlay because we're not adding, we're considering all the overlays we're simulating were done in 2001. So this is a non-structural one, not adding structural value. And the initial IRI would be characteristic of this overlay that's going to be placed in 2022, which for this case was 55 inches per mile. Okay, so this simply shows the threshold values used and the screenshot from Pavement ME. I'm not going to go through these specifically. This is just the values that are used by this agency and or organization for this project. 90% reliability value. Okay, so our rehabilitation design, what did we get? And so this shows the results of making that run for design segment number 4. And what you can see, the left curve is IRI, and this shows the 90% reliability. And then our 2022, where the IRI is reset to the overlay of 55, and then that value is predicted over time. The reason, and this will be very conservative, this will be a conservative through Pavement ME, because Pavement ME assumes that this was done through time 0 at 2001 over a 41-year design frame. And so you can see the IRI is increasing at a steeper rate. This has to do with the site factor. And so this will be conservative, and most users will probably over-predict the IRI from a design standpoint, or at least if I was the designer for this project, that would be okay with me, because I'm not going to under-predict, I'm probably going to over-predict the IRI because of the site factor, 41 years versus 20 years. And once we start getting beyond 20 years for the site factor, it started having a bigger impact on both asphalt as well as Portland cement concrete pavements. So you can see for the rut depth, this would be for the original overlay. After the fractured, we're milling, so we're resetting the overlay, and there's very small rut depths at all. In fact, the average values measured before the overlay in 2022 are very close to what Pavement ME predicted on the average. The bottom-up cracking, there's no bottom-up cracking, none predicted, and we didn't really think there would be. Transverse cracking, this shows the total. And so for segment 4, there's very little transverse cracking predicted over time, which is similar to what was predicted. Very little for the overlay was really measured over time. It was less than about 400 feet per lane mile for the existing 2001 overlay that existed in 2021. This shows top-down cracking. Now, top-down cracking, some does occur. It doesn't exceed the threshold value. You can see when we're milling the surface, removing some of those top-down cracks at the surface. The other thing that you can see is all these cracks are basically confined to the surface. This top graph displays the amount of cracking over time in terms of area, percent total lane area, both before the reset and then after the reset. And then you can see the crack depth for these cracks, top-down cracking, when they start to occur. And basically, it's all confined to the wearing surface, right at the surface. So these cracks do not propagate past, certainly past about 3/4 of an inch, 1/2 an inch to 3/4 of an inch. Most of them are confined to the wearing surface, or half depth to the wearing surface. So strategies to, so I'm going to move on to the last part of the presentation. I'm a little bit over time. Strategies to mitigate reflection cracking. And there's different strategies that can be considered. Interlayer seal coats in Pavement ME. This is a screenshot from Pavement ME. So it's AC over AC with seal coats, AC over AC with interlayers. And we have AC over semi-rigid, AC over JPC, AC or CRCP, AC over JPCP fractured. And so and in the past, from the global calibration of the reflection cracking transfer function, using the LTPP sections, which was done, resulted in almost no difference between whether there were interlayers or seal coats or what for the segments extracted from the long-term pavement performance program. So with and without different strategies to mitigate reflection cracking, what it was telling us, basically there was no impact. So the calibration factors are basically the same between without using interlayers and then using some interlayers and or seal coats. There is no difference. However, with time, some agencies that have used interlayers or seal coats within their own practices and have done calibration and have updated the global reflection cracking transfer function with the calibration coefficients, they have found differences and have shown differences between those asphalt overlays with and without different mitigation strategies. And I wanted to just include, this shows an example of one where the graph on the right is simply for a specific project, and it's the global factors using that are currently in Pavement ME, and we would predict the reflection cracks, transverse reflection cracks of over, with a reliability of over 4,000 feet per mile. That's new and existing transverse cracks. Whereas using the revised agency's calibration coefficients to represent a specific reflection cracking mitigation strategy, these are the new calibration coefficients specific to an organization and agency and to a specific mitigation technique. Now the predicted is slightly above 1,500 feet, almost close to 1,715 feet per mile. A big difference between those. Also, that is what the agency observed, that there is a difference between with and without these different reflection cracking mitigation techniques and or strategies. So I just wanted to mention this, that this is something that some agencies are paying a little bit closer attention to and are finding differences in actually using Pavement ME. So in summary, for this webinar, we did apply the results from the BCP program for rehabilitation design using the BCT in accordance with borings and cores. I hope that all made sense and somehow decisions get made specific to an overlay of fractured, jointed, plain concrete pavement that already had an overlay in place, evaluated the elastic modules results for making decisions and determining a rehabilitation, the strategy. I hope that answered some additional questions and also made sense. Simulating the fractured, jointed, plain concrete pavement with an asphalt surface that already exists, both with load transfer efficiency and the back calculated layer E modulus, as well as specific dates for this project. We hope that made sense. going over, even though we did not spend a lot of time on input level assignment, I hope everyone remembers the difference between the different levels for asphalt over asphalt, asphalt over semi-rigid versus asphalt over some type of concrete, intact or fractured technique. Determine load transfer efficiency. This is a fairly important parameter, has a big impact on how cracks are going to reflect through the overlays. And I hope that made sense. And I hope more users start to measure load transfer efficiency for the transverse cracks in different existing pavements. And then simply overviewed the updates on some of the calibration coefficients regarding inner layers for use in mitigating reflection cracking. That's being paid more attention to now, which I think is good. And I hope more agencies, more organizations actually start to use some of these inner layers, because if they're used under the right conditions, they do make a difference. So with that, I'm going to turn it over to Vooter for our last poll questions. So Vooter, if you would do the last poll questions.
Sure. Yeah, this one, there's 4 questions and some are multiple choice or multiple answer, some are single answer. Poll should now be open. We have about a minute, a little over a minute left. Poll. All right, the poll is now closed. Harold, we can move on to the next section.
I was muted. I guess we'll go on to the question and answer session. And Booter, were there many, and or Clark, were there many questions and those that you haven't already answered?
Yes, there are a few that I kind of waited to the end just to make sure we see what's covered throughout the presentation.
Okay.
And I'll go through them if that's okay with Clark.
Sure.
Proceed.
Okay, so the first question's from Justin Schenkel. His question is, it seems like the BCT is somewhat a requirement. I assume for pavement ME design or using it for rehabilitation. So he's asking if that's correct. And if so, he has concerns. Most of their rehab type projects may not have this level of detail prior to the design. And how can we design using ME if we don't have all of this data?
Good question. The answer to that is it is not a requirement. BCT is not a requirement for pavement ME. Some agencies do use deflection testing as their standard practice. Obviously, not all agencies do. So you can use rehab input level 2, and that's using the distress surveys. You can also use, even if you have an asphalt over Portland cement concrete slabs that are intact, either jpcp, crcp. You can do an unbonded concrete overlay of concrete pavements. You can do a concrete, short jointed plain concrete overlay of flexible pavements. You do not need the BCT as mandatory for the rehabilitation. So it adds additional information that can be considered, but it is not mandatory.
Okay, thanks, Harold. The next one here, it's from Paul McKika. Would fractured JPCP be an appropriate choice to model a severely deteriorated underlying concrete pavement? An example, a concrete pavement that was not specifically rubberized or crack and seeded, but has a low FWD modulus and cores show significant cracking.
Yes, you can. The first part of that question, Vooter, repeat that?
Sure. Would fractured JPCP be an appropriate choice to model a severely deteriorated underlying concrete pavement?
Yes, it could be. Again, it's going to depend on the type of cracks. If this was a jointed plain concrete slab that had multiple mid-slab cracks, there's a limit when you select fractured jointed plain concrete pavement. There's an upper and a lower bounds for the crack spacing, and that would be the only limit. But you definitely could use that fractured jointed plain concrete in simulating, PCC slabs crack that have a lot or additional mid-slab cracks within them. So that definitely would be a possibility to consider.
Okay. And the next one here is, why is the rubberized slab recommended for analysis as 2 layers? Is it just because of how large the fracture pieces are between top half and bottom half of the slab?
Another very good question. The answer to that is yes, especially as I mentioned, jointed reinforced concrete pavements. Most of those that I've evaluated, There is a difference between the thickness above and below the reinforcing steel. In some cases, even for jointed plain concrete, depending upon the size of the aggregate, which comes back to the agency's specifications, there can be a difference. For jointed plain concrete pavements for rubblization, however, I would say it's probably more common for that to be one layer rather than two layers. But this comes back to the agency's specifications on how they specify rubblization.
Next question is related to the BCT and what variables should be used for delineation if there's no stiff layer in a project. I know this one had a bedrock layer that you mentioned, a stiff layer. So how to delineate there's not a stiff layer?
Okay, so this has to do with the segmentation?
That is my assumption, yes.
Okay. And this will be the case for many, many projects where you will not have a stiff layer close to the surface. In other words, if you use EverCalc or the BCT or the back calculation tool, and you have it calculate depth to the rigid layer, there will be projects where that'll be close to or over like 600 inches. And that means you don't need to simulate a rigid layer within the back calculation process. And in that case, you simply don't simulate it. You would segment based on other criteria. It could be thickness. You could segment based on the thickness observations. You could segment based on practical features along the project, whether they be bridges that exist along the project or not. You could also segment based on, obviously, the deflection data, which is what the BCT was originally intended for. So you don't have to segment based on based on the depth of the rigid layer. The only reason I did this for this specific problem is there were definitely abrupt changes, but those abrupt changes really had very little impact on the back calculation of the other layers. And so I went ahead, though, since it was very obvious. That's what I segmented it for this project. But you don't have to do that. You can use other parameters, other site features along the project.
Okay. Next question is, if two existing 9.5 millimeter AC and 19.5 millimeter AC layers are in good condition and merged in an overlay design, which AC material inputs between those two layers do you recommend between the merged layers?
Okay, this if it's for the back calculation process and there's no observed difference, I would combine everything together for the back calculation tool. Once I get to Pavement ME, then I would do this. You want the wearing surface to be simulative of the wearing surface that's in place or going to be in place. So let's say we have a 9.5 millimeter and you have, like it said, 19 millimeter, even with different asphalt contents for the asphalt overlay. So 9.5 millimeter PG 70 minus 28 as the wearing surface. A 9.5 millimeter PG 70 minus 28 as the wearing surface of the overlay. The, let's say, leveling course, or the first layer, couple of layers to be placed on the existing pavement, let's say, are going to be more like a 19 millimeter PG 64 minus 22 asphalt of the overlay. Let's also say that, or for those. So for that overlay, I would have a wearing surface for the overlay, and for the overlay, I would have the layer beneath it. I would treat them as separate layers because of top-down cracking. The gradation index does have a pretty large impact on top-down cracking in terms of fine graded versus coarse graded mixes. And by the way, that was confirmed with some of the SPS 9 segments that were built in the LTPP project. If, on the other hand, let's say I had that exact same condition, but in my existing pavement, I already had an overlay, and I had an overlay, that overlay had stripping. The top 3 inches or 4 inches was a good quality material. The depth, the first 2 inches was stripping for whatever reason. How I would simulate that, I would take the existing asphalt and break it into 2 layers, the good quality and the layer that was exhibiting stripping, and simulate those as 2 layers as they are with the back calculation tool. For the overlay, the new overlay, since I'm limited to 3 layers of asphalt overlay, I would have to only use 1 layer for the new overlay. In that, I would simulate it as the 9.5 millimeter a PG 70 minus 22, because more than likely the surface distresses, the top-down cracking, the transverse cracking at the new transverse cracking at the surface are probably going to control most of the time. And so I would want to use the properties of the wearing surface, since that's going to control what I see at the surface. I hope that makes sense.
Okay, we probably have, depending on how long, we have about 2 minutes left.
Yeah.
But one of them is, oh, Harold, you want to say something?
No, I was just going, we need to leave at least 1 minute to 2 minutes for Clark.
Okay, then, I mean, I don't know if we'll have time for a new one because it's about 2 minutes left. But we will answer these, any questions that were unanswered, and post them on the Pavement ME Design webinar webpage with detailed answers to each one. Okay.
Okay, I would like to point out that this is the last webinar in the current fiscal year, but the new fiscal year begins in about a month. And AASHTOWare will be hosting 4 webinars for the next fiscal year. And we would like to encourage people to submit topics they would like discussed as part of these webinars. And if you could, please submit suggested topics to AASHTOWare or the help desk, and all suggestions will be considered by the task force. And here you see contact information for Pavement ME Design. Ryan Fragapane is the AASHTOWare project manager, and I'm the chair of the task force. And our contact information there. Directly underneath that is the ME Design resource website. That is where all of our webinars are posted, and where Wouter mentioned that any unanswered questions, the answers will also be posted there. We do have the users group meeting coming up at some point in the near future. We hope Jen Albert manages that process. And you see the contact information for the help desk. Again, suggestions for the upcoming webinars can be sent to that address. And we have contact information for our ARA staff. And I think that's it. I'd like to thank everyone for attending. I'd like to thank our presenters. I think it was really well done and presented some really good information. And thanks for everyone for watching and listening and paying attention and submitting the really good questions. Thank you very much.
Thank you, everyone.